Just a quick refresher on interquartile range, something you probably haven't done for quite a while. I've put all of the numbers in order for the checkup, and I circled 89. That's your median. Medians are numbers in the middle. To find your quartiles, all you have to do is cover all of the numbers plus your median up to one side. So there's the median, I cover it and everything to the right, and I find the middle again. The middle of the 4 purple numbers is 75. That's called Q1, your first quartile. And then if I cover the median up and everything to the other side, so there's the median, I cover everything else up, and I find the middle again, that's Q3. A normal range is just the highest minus the lowest. So the normal range here would be 95 minus 62. That's normal. That's what you're used to. Interquartile range is Q3, which is 92, minus Q1, which is 75. So your interquartile range is only 17. Well, today we're going to talk about absolute value, the actual function of it, which means how to graph it and work with it. So just take a second. What would the absolute value parent function look like if it's reflected in the x-axis? So remember, the reflection on the x-axis means that you're going to take it and turn it about the x-axis. So imagine if you could take that graph and fold it on the x-axis. What would happen to that V-shaped graph? What ends up happening is you get this reflection that ends up turning down. So imagine it would kind of look like that. So the dotted green line in this case would be the red line if I could fold it on the x-axis. So this is a transformation summary from the book. So it's what we've been talking about in section 6 versus translation, stretches, compressions, and reflections. They can occur with absolute values as well, where the absolute value symbols act as parentheses. So if you take a look at example 1, they want the graph of the absolute value function, and they want to know how it's different from the parent function. And the parent function for an absolute value is always the same. It's f of x equals the absolute value of x. In letter A, that minus 1 on the outside, that moves your graph down 1. So instead of starting at the origin, it's going to start down 1. That's what we call the vertex of the absolute value, something we'll look at a little later on. From there, your graph is going to go up 1 over 1 on both sides. So I do it a couple times on the right, then I go back to the vertex and do it a couple of times on the left until I have a general V-shaped graph. When you draw the V-shaped graph in, you're going to do it on both sides and try to take it from end of the graph to end of the graph. Meaning, don't make it a tiny V-shaped graph, make it take up the entire grid. In letter B, it's almost the same. 2 changes have occurred. The first, that down 1, is because of the minus 1. But this negative out front, that's a reflection. And it's a reflection in the x-axis. You're not going to reflect a V-shaped graph on the y-axis, so I'll come back to this in a second. What I mean is, if you took that original red graph, so that V-shaped graph you can see that is red right now, and you flipped it on the y-axis, it's still going to be that same red graph. So reflections on the y-axis don't make a difference. Remember, when we reflect on the y-axis, we negate x. So that's what it would look like. You'd have the absolute value of negative x. And a negative inside the absolute value is useless. It's still going to be positive. So reflections on the y-axis don't occur. It's just going to be the x-axis. And those reflections on the x-axis flip our graph upside down. So the down 1 gets taken care of first. Put your vertex down 1. From there, instead of going up and over, go down and over on one side. Then go back to the vertex, go down and over on the other side. So you'll find you've got this V-shaped graph that looks just like the last one, only now it opens down. Anytime you have a reflection, your absolute value graph will open down. In letter B, that plus 3 on the end moves our graph up 3. So I'm going to go up 3 and put my first point, my vertex. Nothing else has changed, so from there I'm going to go up 1 over 1 on one side, go back to the vertex, go up 1 over 1 on the other side, and draw in the V. This one's a little tinier because it started up higher and I ran out of graph, but it is still the same thing. In letter B, I have an up 3 because of the plus 3 and a reflection. Now I'm going to start putting R with a circle just so that I don't have to write out reflection each time, but it is a reflection in the x-axis. So again, I'm going to start by going up 3, but because of that reflection, it's kind of like a negative slope. Because of that reflection, I'm going to go down 1 over 1 on one side then go back to the vertex, go down 1 over 1 on the other side, and then draw the absolute value function in. It's a V-shaped graph. So in letter C, we have two translations going on. I've got a left 1 and an up 4. So this is kind of like battleship to me. Left 1 and up 4 means move left 1 and go up 4 and then put your first point. And from there, count off your slope. Your slope is still going to go up 1 on this side and up 1 on that side. And I'm not going to go up any further because I ran out of room. This absolute value ends up looking like a baby, but it is the same thing. So when you have translations to the left and right, left or right, and up or down, that's when you kind of play battleship, where you move both directions first and then see what's going on with the slope. So in the second one, I've got a left 1 and an up 4, but now I've got a reflection in the x-axis as well. So I'm going to start by going left 1 and up 4, put my vertex there, but now I'm going to go down 1 over 1 a couple of times, back to the vertex, go down 1 the other way over 1 a couple of times. When this happens, when you've got translations going in other directions, your V-shaped graphs don't look as symmetrical because you're taking it from end to end. That's okay. You'll notice some of these will start looking like check marks or upside down check marks. And there's nothing wrong with that. Letter D, I see two movements here. I see a right 3 and an up 2. So right 3 and up 2 puts my vertex in the first quadrant. I don't see any reflections, so I'm just going to go up 1 over 1 on this side. Go back to the vertex, go up 1 over 1 on that side, and using a straight edge, draw in the V. And the second one, still have a right 3 and an up 2, but that minus out front is telling me there's a reflection in the x-axis. So now when I said the right thing and I wrote the wrong angle, or arrow, I'm sorry. So now when I go right 3 and up 2, I'm going to go down 1 over 1 on this side because of the reflection. Go back to the vertex, go down 1 over 1 on this side because of the reflection. Oh my goodness, now I'm a mess, I'm sorry. And then I'm going to draw in the V-shaped graph. Again, it's okay if the sides aren't the same length. I tend to take it from one end of the graph to the next, which is something that will help you considerably in section 8. Even if it kind of looks like a check mark or an upside down check mark, get into that habit. It's a good habit to have. Take a second and do the you try it while pausing the video. So we need to talk about the slope on either side of an absolute value function. If you look at the right-hand side of an absolute value function, the right-hand side is this one, its slope is a positive 1. But how does that relate to the left side? So the left side is this one. And the answer to that is it's the complete opposite. Instead of going up 1 and to the right one, I'm going to go up 1 and to the left one. So you end up getting a positive slope and a negative slope out of the same absolute value function. The only transformation we haven't talked about yet today is the stretches and compressions, and that's how that slope changes. So an absolute value slope will change based on stretches and compressions. In letter A, that 2 is a stretch by 2. I know that it's a stretch because 2 is larger than 1. There hasn't been any left or right movement, so I'm going to start at 0, 0. But from here, I'm going to go up 2 over 1. This 2 is kind of like a slope. So it's kind of like a 2 over 1. I'm going to go up 2 and over 1 on the right, and then I'm going to go back to the vertex, go up 2 over 1 on the left. And so what you'll find is that when you stretch your graph, it gets really skinny. Imagine if you had a V-shaped graph and you were able to vertically pull it up and down at the same time, like something like taffy or a big pile of bubble gum. If you had that and you were able to pull it up from the top and the bottom at the same time, it becomes thinner. Okay, it stretches it out and becomes taller. And that's what happens to these absolute value graphs as well. The complete opposite happens when you start talking about compression. So in letter B, this is compressed by 1/3. And we know that it's a compression because 1/3 is between 0 and 1. It has not moved left, right, up, or down. So I'm going to start at the origin, but now I'm going to go up 1/3. Up 1/3 on both sides. So what ends up happening with a compression, and again, imagine that putty or that silly or that Laffy Taffy or whatever it is that's kind of stretchy, imagine now instead of pulling it up and down at the same time, imagine now if you're squashing it. So you put it between your hands and you're pushing it in on it. That ends up making it flatter. Okay, so stretches will make your absolute value graph much taller, stretch them out, while compressions will push them down and make them flatter. Letter C. Letter C, I see two transformations going on. I see a reflection in the x-axis because of the negative, and I see a stretch by 4. Oops. Okay, so it hasn't moved left, right, up, or down, so started at the origin. But now, because it's stretched and reflected, I'm going to go down 4/1. Go back to the vertex, go down 4/1. So you're going to end up having a really skinny graph that opens down. Reflections and stretches become skinny graphs that open down. Letter D, sorry, there was a little bit of a weird thing going on with the smartboard, but there are two things that are occurring in letter D. We have a reflection in the x-axis because of the negative out front, and a compression by 2/5. And I know that it's a compression because 2/5 is a number between 0 and 1. It has not moved left, right, up, or down, so I'm going to start at the origin. Now I'm going to go down 2/5. Go back to the vertex, go down 2/5. So you'll notice this one is considerably flatter, or fatter, whichever way you want to look at it, than the last one, because it's a compression. Stretches are skinny, compressions are fat. Pause the video and complete the you try it. In letter E, the two transformations that have occurred are a reflection and a stretch by 3. In letter F, it has been compressed. So you'll notice stretches are skinny, compressions are fatter. My only complaint about these two graphs is make sure that your graphs have arrows on the end, because absolute values do keep on going in terms of the ends of them.